Efficient Causal Enhanced Lift Model CEUM for digging potential lift information. Specifically, we first construct contrastive pairs following the properties of the partial order relation of the lifts and maintain structural correlation and consistency during training. Next, we look for a promising average causal effect across batches to get closer to the mean of the estimated individual increase. Finally, we compare the efficiency of the proposed method by performing comprehensive experiments, and the results show that CEUM achieves the most advanced performance on two real-world data sets. A business must choose whether or not to deliver an advertisement to a customer in order to maximize profits and reduce costs. The central difficulty is that we cannot observe both responses of a unit when receiving a certain treatment or not simultaneously, commonly known as the fundamental problem of causal inference. Uplift modeling is a standard predictive method for such tasks and seeks to predict the causal effect of an intervention/treatment on a specific outcome at the individual level. In this work, we proposed a causal enhanced uplift model, CEUM, to alleviate the general problem of lack of information on uplift. We introduce a new enhancement loss function relative to implicit prior information about enhancement both at the individual and group level. Specifically, we use the relationship of partial order of improvement between pairs of positive and negative samples and the uniformity between mean individual improvements and group treatment effects. To the best of our knowledge, this is the first attempt to use elevation information implicit in the neural network elevation model, and the main architecture is simple and universal. Our proposed method is validated on two real-world data sets. The results, experimental data, show that the proposed model has reached the state of the art. The contributions of this work are summarized below. We present a novel enhanced causal model of lifting to capture both the partial ordering relationship of contrastive pairs and the average constraint of lifting. The two proposed components improve the estimation capacity of the causal effect by using and taking advantage of previous information, both individual and global, of the increases. We evaluated the proposed model using two diverse public real-world data sets and observed improvements over state-of-the-art benchmark methods.
Proposed method. The general description of the CEUM architecture is illustrated in Figure 1 and can be considered as a multitasking model, which includes a main task and two auxiliary tasks. Construction of pairs. Essentially, we hope to use the enhancement model to categorize the population into four subsets as shown in Fig. 2a. The sure things are individuals who always respond, regardless of whether they receive treatment or not. Aiming for sure things does not generate additional returns, so these types of people have zero improvement. Persuadables are individuals who will be more likely to respond because they are exposed to a treatment. These people are exactly the target population that we must distinguish. These types of people have a positive elevation. Do not disturbs are people who have become less likely to respond due to treatment. Obviously, targeting them has no benefits, but it does bring big additional costs. These types of people have a negative elevation. Lost causes are people who never respond, regardless of whether or not they receive the campaign. Since the treatment of lost causes will not generate additional income, these types of people do not have any benefit. However, for real-world data sets, it is not practical to figure out these four categories. Usually, using the available data, we categorize the population as illustrated in Figure 2b. G1 are individuals who are treated and respond. A unit in G1 can belong to persuadables or safe things. G2 are individuals who are in the control group and respond. A drive in G2 can belong to safe things or do not disturb. G3 are individuals who are treated and do not respond. A unit in G3 may belong to lost cause or do not disturb. G4 are individuals who are in the control group and do not respond. A unit on G4 can belong to either persuadable or lost causes.
2. Experiment. The Hillstrom email advertising dataset, 8, includes data tracked in a randomized trial following an email advertising campaign. Clients were evenly distributed into 2 treatment groups and a randomized control group. We choose to receive a women's merchandise email as treatment, and the result is the visiting status of customers. 3. Results. We report the results on the validation set drawn from Hillstrom in Figure 3. Figure 3a shows the elevation curves on the Hillstrom data set, the higher the better. Likewise, we can observe that our approach achieves a higher and more stable AUC, which demonstrates the effectiveness of our method. Figure 3b shows that both extremely small and large margin 1 will destroy performance, and Figure 3c demonstrates that margin 2 trends as AUC fluctuates. From Fig. 3d and 3e, we conclude that it is beneficial to extend the lifting distance of the pairs appropriately, but if the penalty is too large, the model will shrink extremely, and LATE can help limit the improvement to a reasonable extent on average. However, when beta is large, it risks homogenizing the increases and weakening the classification capacity. In addition, our method benefits from larger batches and more training. 4. Conclusions. We introduced a new multitasking framework for the Uplift model. The proposed model alleviates the lack of direct supervision or explicit labeling for the survey, which precedent supervised classifiers often suffer from. CEUM constructs a sequence of pairs by randomly sampling from opposite subsets, exploiting the partial order relationship for instances between subsets. In addition, CEUM performs the ATE correction simultaneously with the aim of progressively reducing the prediction deviation. Experiments on 2 real-world data sets demonstrate its promising effectiveness and exceed competitive baselines.